Hi, I'm Alex. Tonight we turn to a quiet power that never leaves you gravity. It anchors your body, cradles the air around Earth, and silently choreographs planets and galaxies across unimaginable distances. Yet the deeper truth is far more unsettling. Gravity isn't really a force at all, but something stranger, deeper, and more beautiful than we're taught. If this kind of exploration draws you in a soft like or subscribe, helps keep these journeys alive. Now let's begin. Right now, at this very moment, you're floating in mid-air. No, really. The chair beneath you, the floor under your feet, they're pushing up against you with a force of 150 to 220 pounds. That sensation you call weight, it's not gravity pulling you down. It's the ground crushing you upward. You're being compressed, squeezed, pressed against, not pulled. And here's the part that's going to blow your mind. Isaac Newton, one of the greatest geniuses in human history, got it fundamentally wrong about gravity for 228 years. Everything you learned in school about gravity, incomplete, the apple falling from the tree, didn't happen the way you think. You've been carrying a beautiful lie in your head since first grade, and tonight we're going to shatter it. Consider the apple. You've been told it falls because Earth's gravity pulls it downward. A force reaching up from the planet, grabbing the apple, yanking it to the ground. Makes perfect sense, right? Except that's not what's happening at all. The apple isn't being pulled. It's following its natural path through curved space. It's doing exactly what it wants to do, traveling in what it considers a perfectly straight line. The ground. The ground is what interferes. Electromagnetic forces from the soil and grass stop the apple's journey. The ground blocks it. From the apple's perspective, it's minding its own business, and the earth rudely gets in the way. Think about that. The entire foundation of what you learned in elementary school, gravity, as a pulling force, misses the deeper truth. It's like saying the earth is flat because it looks flat when you're standing on it. Works for everyday purposes. Gets you through life, but completely wrong about the fundamental nature of reality. Newton figured out the mathematics of gravity in 1687. His book, The Principia, changed everything. Before Newton, people guessed about why things fell. He showed them. The same mathematics that describes an apple falling also describes the moon orbiting Earth and Earth orbiting the sun. Revolutionary. People thought the heavens operated under different rules than Earth. Newton unified them with one elegant set of equations, and those equations worked brilliantly. They predicted planetary motion with incredible accuracy. They explained ocean tides, the water rising and falling, because the moon's gravity pulls on it. They let scientists discover new planets by observing tiny irregularities in known orbits. That's how Neptune was found in 1846. Astronomers noticed Uranus wasn't moving exactly as Newton's equations predicted. They calculated where an unknown planet would need to be to cause those deviations. They pointed their telescopes at that spot. There was Neptune, exactly where the math said it should be. Pure prediction, pure triumph. For over 2 centuries, Newton's laws reigned supreme. But there was a problem, a small one. Mercury's orbit. Mercury orbits the sun in an ellipse that slowly rotates over time, what astronomers call precession. Newton's equations predicted how much Mercury should precess based on the gravity of other planets. But observations didn't match. Mercury was precessing about 43 arc seconds, more per century than predicted. That's roughly 1/180th of a degree per century. Incredibly small, like a kid misbehaving by running off course 1 millimeter every 100 years, but real, measurable, and enough to keep scientists awake at night. They searched for explanations. Maybe an undiscovered planet called Vulcan was pulling on Mercury. Didn't exist. Maybe Newton's laws needed tweaking. Nothing worked. The mystery remained unsolved until 1915. Enter Albert Einstein. His insight was radical, revolutionary, reality-shattering. Gravity isn't a force at all. It's the curvature of space-time itself. Space-time, not space and time. Space-time, a single unified, four-dimensional fabric. And massive objects don't pull on other objects. They bend this fabric. They curve it. Earth curves space-time around it. The sun curves it more. Even you curve space-time a tiny amount. Everything with mass or energy warps the geometry of reality itself. Picture space-time like a stretched rubber sheet. Though in reality, there's no actual sheet. It's just the best metaphor we've got. Place a bowling ball on that sheet. It creates a depression. Roll a marble nearby. The marble doesn't travel in a straight line. It curves toward the bowling ball, following the slope of the depression. From the marble's perspective, it's following the straightest path available. But because the sheet is curved, that path curves toward the ball. That's gravity, not a force. Geometry. The last time you stumbled and fell, that sensation of the horizon tilting the world spinning, that was your brain desperately trying to make sense of curved space. You weren't feeling gravity pull you down. You were feeling yourself follow a geodesic through warped space-time, while your inner ear screamed in confusion. Why did it take 228 years to realize Newton was wrong? Because for everyday situations, apples, baseballs, even satellites, Newton's equations work perfectly. The difference only shows up in extreme situations. Strong gravity, high speeds, Mercury's close to the sun, orbiting fast, experiencing stronger space-time curvature than any other planet. That's where Newton's approximation broke down. Here's another way to think about it. Ever driven into a sharp curve at high speed, you feel thrown outward, right? Flung toward the outside of the turn. But actually, you're trying to go straight. Your body wants to continue in a straight line through curved space. The car door, the seat belt, they're forcing you to curve. Just like the ground forces you to curve away from your natural geodesic. And GPS, back in the 1980s, finding your way meant paper maps folded wrong in the glove compartment. Today's GPS pinpoints your location to within meters. What changed, Einstein? GPS satellites orbit high above Earth, where space-time is less curved, so time runs slightly faster, 38 microseconds per day, faster than on the ground. Without correcting for Einstein's predictions, GPS would be off by 11 kilometers within a single day. Every time you navigate with your phone, you're proving Einstein right and Newton incomplete. Mercury, that misbehaving planet, Einstein's equations predicted its precession exactly, 43 arcseconds. Perfect match. But if there's no pulling force, if gravity is just curved, space-time, why do astronauts float? Why does the moon orbit Earth instead of flying off into space? The answer will make you rethink everything you thought you knew about standing, sitting, and the very ground beneath your feet. The International Space Station orbits 400 kilometers above Earth, about 250 miles up. Astronauts float inside, drifting from wall to wall, turning somersaults in midair. You've seen the videos. They look like they've escaped gravity, entirely floating in 0 G because they're in space. Wrong. Gravity at the ISS is still 90% as strong as it is on the ground. If you could somehow stand on the station's hull, you'd weigh almost as much as you do right now. The astronauts aren't beyond Earth's reach. They're not floating because gravity disappeared. They're falling continuously, constantly, at 28,000 kilometers per hour. That's roughly 17,500 miles per hour. They fall toward Earth, but they're also moving sideways so fast that they keep missing it. Earth curves away beneath them at exactly the rate they fall toward it. They circle the planet every 90 minutes in a perpetual state of free fall, never hitting the ground. And that's why they're weightless. Not because there's no gravity, because nothing's pushing on them. Let's run a thought experiment. Picture yourself in an elevator. Normal situation. You're standing on the floor. The floor pushes up against your feet. That push, that resistance, is what you call weight. It's the sensation of the floor, preventing you from following your natural geodesic through curved space-time. Now imagine someone cuts the cable. Horrible scenario, but stay with me. The elevator falls, and you float inside it. You don't feel the floor anymore. You're weightless. The elevator's falling. You're falling both at the same rate. Relative to the elevator, you drift. You experience exactly what astronauts experience in orbit. Einstein called this the equivalence principle, one of the foundational ideas of general relativity. Two situations that seem completely different, floating in deep space, far from any planet, and falling in an elevator with a cut cable, produce the exact same sensation. You can't tell the difference from inside. They're equivalent. Standing still on Earth, the floor pushes you up. You feel weight. Accelerating in a rocket in deep space at 9.8 meters per second squared, the rocket floor pushes you up in exactly the same way. Same sensation. Can't tell the difference. Free fall on Earth, weightless. Floating in deep space with no planets nearby, weightless. Same experience. Equivalent. This brings us to geodesics, the paths objects follow through curved space-time. Think of a flight from New York to Tokyo. Look at it on a flat map. The route curves up over Alaska. Seems indirect. Why not fly straight across the Pacific? Because Earth isn't flat. On a globe, that Alaska route is actually the shortest path. It's what's called a Great Circle route. Looks curved on a map, but it's the straightest possible path on Earth's curved surface. Space-time works the same way. Earth orbits the Sun. It's not being pulled by a force. It's following a geodesic, the straightest possible path through space-time, curved by the Sun's mass. From Earth's perspective, it's moving in a straight line. But because space-time is curved, that straight line from our outside perspective looks like an orbit. The planet is falling toward the Sun constantly, but moving sideways fast enough that it keeps missing. Just like the ISS falls toward Earth, but keeps missing. Free fall. The natural state of motion, every object in the universe, unless something interferes, follows geodesics through curved space-time. You sitting in that chair, you're trying to follow a geodesic toward Earth's center. The chair stops you. It pushes you up away from your natural path. That's why you feel weight. Time dilation makes things even stranger. Time doesn't pass at the same rate everywhere. The stronger the gravitational field, the more curved the space-time, the slower time passes. GPS satellites orbit about 20,000 kilometers above Earth. Up there, space-time is less curved than down here. Time runs faster, specifically 38 microseconds faster per day than clocks on the ground. Doesn't sound like much, but light travels 300 meters per microsecond. Without correcting for this time difference, GPS would accumulate errors of about 11 kilometers per day. Your navigation would be worthless. During the Gulf War in 1991, GPS guided precision strikes with unprecedented accuracy. That accuracy depended entirely on Einstein's equations. Soldiers in the desert calling in coordinates, relying on satellites whose clocks run faster than theirs because of curved spacetime. Einstein won that war as much as any general. Stand on top of a mountain. Time passes faster for you than for someone at sea level. The difference is incredibly tiny. We're talking nanoseconds per day, but it's real. You age faster at higher altitudes. Not noticeably, not meaningfully, but measurably. Your wristwatch on your arm runs slower than a clock on the shelf. The watch is closer to Earth's center, deeper in the gravitational well, experiencing more curved space-time. Science, not advertising. In 1919, astronomers tested Einstein's prediction that light should bend around massive objects. During a solar eclipse, Arthur Eddington led expeditions to photograph stars near the sun's edge. Normally, the sun's glare overwhelms starlight, but during totality, you can see stars. If Einstein was right, the sun's mass should curve spacetime, and starlight passing near the sun should follow that curvature. The stars should appear displaced from their actual positions. They were about 1.8 arc seconds, less than 1/2000th of a degree, but measurable, exactly matching Einstein's predictions. The next day, Einstein was world famous. The New York Times ran the headline, "Lights all askew in the heavens." The scientific establishment went wild. General relativity had made a specific, testable prediction, and nature confirmed it. Today, gravitational lensing is a standard astronomical tool. Massive galaxy clusters between us and distant galaxies bend light, creating multiple images, arcs, rings. We use these distortions to map dark matter stuff that doesn't emit light but does curve space-time. We can see dark matter's gravitational fingerprints, even though we can't see dark matter itself. Astronaut Scott Kelly spent nearly a year aboard the ISS. His identical twin brother Mark stayed on Earth. When Scott returned, he was younger than Mark, not by much, by 8.6 milliseconds, but younger, measurably. Time passed more slowly for Scott in orbit because he was moving fast and experiencing slightly less gravity. Time dilation is real. Twin paradox confirmed. In 2010, scientists placed two atomic clocks vertically separated by just 33 centimeters, 13 inches. One clock ran faster than the other. They could measure time dilation over a height difference smaller than a footstool. Stunning precision. High-frequency trading firms synchronize their computers to nanosecond precision. Milliseconds mean millions of dollars. They have to account for the fact that clocks at different altitudes run at different rates. Einstein's equations govern Wall Street. Want to live a few extra milliseconds? Climb onto your roof. Your spouse might think you've lost it, but science supports you. You'll age infinitesimally faster up there, experiencing more time before you die. The universe is weird like that. If you're thinking, this is insane, congratulations, your brain is working normally. Evolution built your intuition for throwing spears and avoiding tigers. not for understanding relativistic physics, but the universe doesn't care what your brain finds intuitive. Reality operates on its own rules, and those rules are strange. But this is just the appetizer. When space-time curves to its absolute extreme limits, something forms that devours everything, even light itself. A black hole isn't a hole. It's a region of space-time curved so insanely, so violently, that nothing can escape. Not matter, not light, not information. Once you cross a certain boundary, every possible path through space-time leads inward. There's no way out. Not because something's pulling you, because the geometry itself makes escape impossible. That boundary is called the event horizon. It's not a physical surface, not a wall you can touch. It's a point of no return defined purely by geometry. Cross it, and your future points inward toward the center, as surely as your future in normal space-time points forward in time. Your future inside a black hole points toward the singularity. Black holes form when massive stars die. A star is a balanced nuclear fusion, pushing outward versus gravity crushing inward. As long as fusion runs, the star survives. But eventually, a massive star exhausts its fuel. Fusion stops. Gravity wins. The core collapses in less than a second. If the star is massive enough, more than about 20 times the sun's mass, the collapse doesn't stop. Nothing can resist it. The core compresses beyond neutron star density. It becomes a black hole, a singularity surrounded by an event horizon. For a black hole with the sun's mass, the event horizon would be about 3 kilometers in radius, 10 solar masses, 30 kilometers. A supermassive black hole with 1 billion solar masses, like the ones at galaxy centers larger than Saturn's orbit, nearly 3 billion kilometers across. Wrap your head around that. Fall toward a black hole feet first, and you experience something terrifying called spaghettification. Your feet are closer to the black hole than your head. Gravity pulls harder on your feet. The difference in pull, the tidal force stretches you, slowly at first, then faster, then violently. You elongate like a noodle, your body pulled into a thin strand. For a small black hole, spaghettification happens before you reach the event horizon. You're torn apart in the approach, shredded, stretched until molecular bonds snap. For a supermassive black hole, the tidal forces at the horizon are gentle. The horizon is so far from the center that the curvature gradient is gradual. You could cross the event horizon intact, comfortable even. You'd only get spaghettified much later, deeper in as you fall closer to the singularity. Here's where it gets truly bizarre. Time behaves differently depending on who's watching. From your perspective falling in, you cross the event horizon in finite time. Seconds, minutes, depends on the black hole's mass. You pass through. Nothing special happens at that moment. No sign saying you are now doomed. Just continued falling. But from your friend's perspective, watching from a safe distance, you never quite cross. As you approach the horizon, time dilation becomes more and more extreme. From their viewpoint, time for you slows down, and slows, and slows, asymptotically approaching zero at the horizon. They see you freeze, moving slower and slower. Your clock ticks slower. Your movements become glacial. The light from you shifts redder, gravitational redshift, moving from visible light to infrared, to radio waves, dimming, fading. Eventually, you become so dim and so redshifted that you vanish from view, but you never actually cross. Not from their perspective. You're frozen at the edge, forever fading like a ghost. Both perspectives are correct. That's the paradox. You experience crossing. They never see you cross. Relativity allows both to be true simultaneously because there's no universal now coordinating the universe. In 1974, Stephen Hawking shocked the physics world. He predicted that black holes aren't completely black. They emit radiation. Quantum effects near the event horizon create particle-antiparticle pairs. Normally, these pairs annihilate instantly. But near a black hole, one particle might fall in while the other escapes. From outside, it looks like the black hole is radiating. This radiation, Hawking radiation, carries energy away. The black hole loses mass. Slowly, incredibly slowly. A black hole with the sun's mass would take about 10 to almost 67 years to evaporate completely. That's 10 with 67 zeros after it. For comparison, the universe is only about 10 years old. But smaller black holes evaporate faster. A black hole with a mountain's mass, about 1 billion years. A black hole the mass of a battleship. It would explode in a fraction of a second, releasing energy equivalent to thousands of nuclear bombs. September 14th, 2015, 5:51 a.m. Eastern Time. 2 detectors in Louisiana and Washington State picked up a signal. Gravitational waves, ripples in space-time itself swept through Earth. 2 black holes, 29 and 36 times the sun's mass, had spiraled into each other 1.3 billion light-years away. As they orbited each other, they emitted gravitational waves, losing energy, spiraling inward, faster and faster. In the final tenth of a second, they merged. The resulting black hole was 62 solar masses. Wait, 29 plus 36 equals 65. What happened to 3 solar masses? Converted entirely into gravitational wave energy. E over mc2, 3 times the sun's mass, transformed into pure space-time ripples. For that brief moment, 1/10 of a second, the merger released more power than all the stars in the observable universe combined. 50 times the light output of every star everywhere all at once, but in gravitational waves, invisible to normal telescopes. Where were you on September 14th, 2015, having coffee, driving to work, sleeping? While you went about your morning space-time itself shuddered. Ripples from a cataclysm 1.3 billion years ago passed through your body, stretching and squeezing you by about 1,000th the diameter of a proton. You didn't notice, but it happened. At the center of our Milky Way galaxy lurks Sagittarius A, a supermassive black hole, 4 million times the sun's mass. We've tracked stars orbiting it for decades. One star S2 completes an orbit every 16 years. At closest approach, it reaches 2% the speed of light. Only a black hole could create such an intense gravitational field in such a small region. In 2019, the Event Horizon Telescope, a planet-sized network of radio dishes, imaged the black hole at the center of galaxy M87 55 million light-years away. They captured the black hole's shadow, a dark circle surrounded by a glowing ring of superheated gas. The size and shape matched Einstein's predictions exactly. LIGO's technology measuring distances to within a tiny fraction of a proton's width has spun off into military applications. Seismic sensors, vibration detectors, precision instruments, born from the quest to hear black holes colliding across cosmic distances. If you fall into a black hole, the good news, you'll see the entire future of the universe fast-forwarded before your eyes. Light from outside keeps reaching you, compressed and blue-shifted. The bad news, you've only got about 3 seconds before spaghettification tears you into subatomic ribbons. So enjoy the show while it lasts. But black holes are just supporting actors. The thing that dominates the entire universe, that controls its past, present, and future, is stranger by far. 13.8 billion years ago, space-time began. Not something exploded into space. Space itself came into existence. Time started ticking. Before that moment, there was no before. Asking what came before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense. Time is part of the universe. When the universe began, time began. No earlier moment existed. The Big Bang wasn't an explosion in space. It was the expansion of space itself. Every point in the universe moving away from every other point. Not because things are flying apart through static space, but because space itself is stretching. Like dots on an inflating balloon. The dots don't move across the rubber. The rubber between them expands. We have baby pictures of the universe. The cosmic microwave background. Radiation from when the universe was only 380,000 years old. Light from that era has traveled 13.8 billion years to reach us, redshifted by expansion into microwave wavelengths. We can map tiny temperature variations across the ancient sky, seeds of structure, regions that would eventually collapse into galaxy clusters. For most of the 20th century, astronomers assumed the universe's expansion was slowing down. Gravity from all the matter should be pulling everything back together, they thought. Maybe slowly enough that expansion continues forever. Maybe fast enough that it eventually reverses, collapsing everything back in a big crunch. But definitely slowing. 1998 changed everything. Two teams studying distant supernovas made a discovery nobody expected. The universe's expansion isn't slowing down. It's speeding up, accelerating, like throwing a ball upward and watching it fly away faster and faster instead of falling back. Impossible. Violates everything we thought we knew. But the data was clear. Distant supernovas were dimmer than they should be, farther away than expected. Something is pushing space apart, counteracting gravity, causing expansion to accelerate. We call this something dark energy. We have no idea what it is. It might be a property of empty space itself, a cosmological constant Einstein originally proposed for different reasons. It might be a dynamic field permeating space. We don't know, but it makes up approximately 68% of the total energy content of the universe. 68% of everything is something we can't see, can't detect directly, and don't understand. And there's more mystery. Galaxies rotate faster than they should, based on visible stars, and gas outer regions should move slower. But they don't. They move too fast. The only explanation, additional mass we can't see. Dark matter. It doesn't emit light, doesn't absorb light, doesn't interact electromagnetically at all. We only know it exists because of gravity. Its mass curves spacetime. We can see that curvature's effects on visible matter and on light passing through. Dark matter makes up about 27% of the universe. It's everywhere. A halo of it surrounds our galaxy. Billions of dark matter particles pass through your body every second. Right now, you don't feel them. They pass through normal matter almost without interaction. Ghosts flooding through you constantly. Here's the accounting. Normal matter stars, planets, gas dust, people, everything made of atoms makes up roughly 5% of the universe. 5%. Dark matter is 27%. Dark energy is 68%. We understand 5% of what exists. The other 95%, total mystery, like standing on a beach at night, waves rolling in. You see the foam, the white caps, maybe 5% of the water. The other 95%, the dark ocean beneath you. Sense its presence, feel its power, but can't see it. That's our universe. In 4 billion years, the Andromeda Galaxy will collide with the Milky Way. Don't worry, you won't be around. Neither will Earth, probably. The Sun will have expanded into a red giant, by then likely consuming our planet. But if somehow you were watching the night sky, would be spectacular. The collision unfolds over hundreds of millions of years. Stars rarely hit each other, too much space between them. But gas clouds compress, triggering massive bursts of star formation. The sky blazes with newborn stars. The two galaxies distort, stretching into tidal tails, then merging into a single giant elliptical galaxy. Fast forward to 100 billion years from now, every galaxy beyond our local gravitationally bound group has disappeared beyond the cosmic horizon. Expansion has carried them so far away that their light can no longer reach us. An observer then would look out and see only one galaxy in an otherwise empty universe. They'd have no way to know the universe was ever larger, no way to discover the Big Bang or cosmic expansion. All the cosmological evidence we have today would be unavailable. They'd be observationally cut off from the truth. We're fortunate to exist when we can still see the broader universe. In trillions of years, star formation stops. All available gas used up or expelled. Existing stars burn out. White dwarfs cool to black dwarfs. Neutron stars remain. Black holes slowly evaporate through Hawking radiation. Eventually, vastly far in the future, even black holes evaporate completely. The universe becomes a thin soup of particles and radiation spreading through ever-expanding space. Heat death, maximum entropy, the final state. But that's unimaginably far ahead. For now, the universe is vibrant. Stars forming, galaxies colliding, black holes growing, and we're here trying to understand it all. In 2024, the James Webb Space Telescope detected galaxies from 13.5 billion years ago. Light that's been traveling almost since the Big Bang. We're looking back in time, seeing the universe as a cosmic infant, galaxies forming, stars igniting for the first time. Imagine being born 100 billion years from now. You'd look up and see one galaxy. You'd think that was everything, the entire universe. You'd have no evidence it was ever larger, ever different. Your cosmology would be fundamentally limited by observation. The universe would hide its own history from you. Dark matter research has spawned ultra-sensitive detectors, now used in medical imaging. Technology developed to catch rare particle collisions deep underground has medical applications. Science for understanding the universe pays unexpected dividends. Some physicists theorize dark energy might not be constant. It might strengthen over time. In about 22 billion years, it could tear space-time apart. The Big Rip. First galaxy clusters unbind, then galaxies themselves, then solar systems, then planets, then atoms. Eventually, space-time itself shreds, everything pulled apart by accelerating expansion. Speculative, uncertain, but possible. 95% of the universe is mystery. It's like being married for 40 years and still having no idea what your spouse is thinking, except the universe is less communicative. If this story makes you feel small and insignificant, congratulations. You're approaching truth. We're tiny, Our planet is a speck, our galaxy one among hundreds of billions, and we only understand 5% of what's out there. But wait, the next part will make you feel magnificent again, because humanity, hairless primates, on a small rock has accomplished something absolutely extraordinary. In 1971, scientists put atomic clocks on commercial airplanes and flew them around the world. When the planes landed, those clocks were ahead of identical clocks that stayed on the ground by nanoseconds, exactly the amount Einstein's equations predicted. Time dilation, real. Measured, confirmed. In 2010, scientists placed 2 atomic clocks separated vertically by 33 centimeters, about 13 inches, 1 tick of difference per lifetime. No, they measured time dilation over that tiny height difference immediately. Stunning precision. September 2015, LIGO detected gravitational waves. The measurement required detecting a change in distance smaller than 1/10,000th the diameter of a proton. A proton is already 100,000 times smaller than an atom. LIGO measured changes far smaller than that, like measuring the distance from Earth to the nearest star to within the width of a human hair. April 2019, the Event Horizon Telescope revealed the first image of a black hole's shadow, M87, 55 million light-years away. The size, shape, brightness, everything matched predictions Einstein made in 1915. 104 years later, we photographed exactly what his equations described. Every test confirms general relativity. Every measurement matches predictions. From the lab bench to the cosmos, Einstein's geometric description of gravity holds. But we know it's incomplete. General relativity describes the large stars' galaxies' space-time curvature on cosmic scales. Quantum mechanics describes the small atoms' particles, the subatomic realm. Both theories are spectacularly successful. Both have been tested to extraordinary precision, and they contradict each other. In normal situations, not a problem. Quantum mechanics handles small stuff. General relativity handles big stuff. They rarely overlap, but in extreme conditions inside black holes at the Big Bang's first instant, both matter. Gravity is strong. Scales are quantum. We need both theories working together, except they don't work together. Apply both simultaneously, and you get nonsense, infinities, mathematical breakdowns. The equations blow up. At a black hole's singularity, space-time curvature becomes infinite. But at such small scales, quantum effects must dominate. We need quantum gravity, a theory unifying both frameworks. We don't have one. String theory proposes that fundamental particles aren't points but tiny vibrating strings. Different vibration patterns create different particles. Gravity emerges naturally from one vibration mode. The theory requires 10 or 11 dimensions, most curled up, too small to see. Mathematically elegant, but experimentally, no confirmed predictions yet. Loop quantum gravity takes a different approach. It quantizes space-time itself, treating it as a network of discrete loops rather than smooth continuum. Space and time come in indivisible chunks at the smallest scales. This might eliminate the infinities, but it also struggles to make testable predictions. Other theories exist: higher dimensions, emergent gravity, questioning whether space-time is fundamental. We don't know which, if any, is correct. Quantum gravity remains one of physics' biggest unsolved problems. The 2030s will bring LISA, the Laser Interferometer Space Antenna, 3 spacecraft in a triangle with sides 5 million kilometers long, orbiting the Sun. It'll detect lower frequency gravitational waves from sources LIGO can't see, supermassive black holes merging at galaxy centers, events that take years to complete producing waves LIGO's too sensitive to detect. Lisa will hear them. The Event Horizon Telescope is upgrading. Soon we'll have movies of black holes watching matter spiral inward in real time, seeing space-time dynamics play out, testing general relativity in its most extreme regime. Scientists are searching for primordial gravitational waves, ripples from the Big Bang's first moments. If inflation happened, a period of exponential expansion in the universe's first fraction of a second, it would have generated gravitational waves. Finding them would confirm inflation reveal the energy scale of the early universe and potentially point toward quantum gravity. Some physicists think we might detect evidence of a multiverse if our universe is one among many collisions between universes might leave signatures we could observe, speculative, far-fetched. But within the realm of possibility, here's something that should blow your mind. You are made of stardust, not metaphorically, literally, the carbon in your cells, the oxygen you breathe, the nitrogen in your DNA, the calcium in your bones, the iron in your blood. Every atom heavier than helium was forged in stellar furnaces, created in the cores of massive stars through nuclear fusion, then scattered across space. When those stars exploded as supernovas, the atoms in your body are older than Earth, older than the sun. They've been recycling through the cosmos for billions of years. They've been part of nebulas, molecular clouds, previous stars, previous planets. Now they're part of you. Temporarily, when you die, they'll return to the universe, eventually incorporated into something else. You're not separate from the universe. You're a temporary arrangement of cosmic matter that has organized itself into a form capable of contemplating its own existence. Think about what humanity has achieved. We're hairless apes on a small planet orbiting an ordinary star in an ordinary galaxy. Yet we've figured out fundamental laws governing reality across 93 billion light years. We've measured gravitational waves from events 1.3 billion light years away. We've photographed black holes at galaxy centers millions of light years distant. Einstein said, "The most incomprehensible thing about the universe is that it's comprehensible." We're tiny creatures. The universe is vast. Yet we understand it. Not everything. Not yet. But the fundamental principles, the deep structure, we've got those. Right now, you're moving through four-dimensional space-time. You're not standing still. You're accelerating upward against your natural geodesic. The ground pushes you with 150 to 220 pounds of force. That's weight. That's the sensation preventing you from falling freely through curved space-time. You're surfing the geometry of the cosmos. How cool is that? Next time you look at the moon, remember it's falling around Earth endlessly, and you're standing on a rock that's falling around the sun in a galaxy, falling toward mysteries we're still unraveling. In 2024, physicists made breakthroughs on the black hole information paradox. New insights suggest information isn't lost. It's encoded holographically at the event horizon. Quantum entanglement might be the key. We're closing in on answers. The Alcubierre drive, a theoretical warp drive that contracts space ahead of a spacecraft and expands it behind might allow faster than light travel without violating relativity. You're not moving through space faster than light. Space itself moves around you. The math works. The engineering requires exotic matter with negative energy density. Might not exist, but we're exploring possibilities. Future civilizations might communicate via gravitational waves. Light gets absorbed by dust and gas. Gravitational waves pass through almost unimpeded. Modulate them correctly, and you could send messages across the galaxy, slower than light, but unstoppable. A 2023 experiment linked quantum entanglement with gravity, suggesting they're aspects of the same underlying reality. This might point toward the unified theory we're seeking: quantum mechanics and gravity married at last. Now you know you're not being pulled down, you're being pushed up. Next time your boss yells at you for being late, tell them, "I'm resisting curved space-time. Give me a break." Here's the final message, the most important one. You're not insignificant. You're the universe becoming aware of itself. 13.8 billion years of cosmic evolution produced eyes capable of looking back at the Big Bang, minds capable of understanding black holes, consciousness capable of grasping its own existence within curved space-time. This knowledge won't make you rich, but it makes you free. Free from ignorance, free from the illusion that you're just a passive observer. You're an active participant in the cosmic story. The universe is unimaginably vast, but there's only one you, one unique arrangement of stardust that thinks, feels, understands. That's not small, that's miraculous. You're not standing still on flat ground with gravity pulling you down. You're accelerating through four-dimensional space-time, held aloft by electromagnetic forces surfing a geodesic through the curved fabric of reality itself. You're riding the geometry of the cosmos, and that, my friend, is the truth about gravity. Now that you understand what gravity really is, curved spacetime, not a pulling force, let's see it in action. Because gravity doesn't just make apples fall, it sculpted everything around you: your planet, your solar system, the very atoms in your body. Start with the sun, the king, the absolute monarch of our neighborhood. The sun contains 99.86% of all mass in the solar system. Everything else, Jupiter, Saturn, Earth, Mars, all the other planets, moons, asteroids, comets, dust, makes up the remaining 0.14%. The sun dominates so completely that it curves space-time in a radius stretching 5 billion kilometers. That's beyond Pluto's orbit. 8 planets follow geodesics through that curved space-time. They're not being pulled. They're doing what comes naturally, traveling in straight lines through geometry that isn't straight. Here's something wild. If the sun suddenly vanished, poof gone, Earth wouldn't know for 8 minutes and 20 seconds. That's how long light takes to travel from the sun to Earth. Gravity propagates at light speed. For 8 minutes, we'd continue orbiting nothing following the old curvature. Then space-time would flatten, and Earth would shoot off in a straight line, carrying us into the frozen darkness of interstellar space. Pleasant dreams. Earth itself is a product of gravity. 4.5 billion years ago, a cloud of dust and gas left over from earlier stellar deaths began to collapse. Gravity pulled it inward. As it contracted, it spun faster. Conservation of angular momentum. The center grew hot and dense enough to ignite fusion. The sun was born, but plenty of material remained in a disk around the young star. Dust particles collided and stuck together. Millimeter-sized grains became centimeter-sized pebbles. Pebbles became rocks. Rocks became boulders. Boulders became planetesimals, objects kilometers across. And planetesimals, with their own gravitational pull, swept up everything nearby. In the chaos of the early solar system, these growing protoplanets smashed into each other, merged, shattered, merged again. Gradually, a few winners emerged, the planets we know today. As Earth grew, gravity sorted material by density. Heavier elements sank toward the center. Iron and nickel, the densest common materials, descended to form the core. Lighter silicates rose to form the mantle and crust. This process, differentiation, gave Earth its layered structure. The iron core does something crucial. It's liquid hot enough to flow, but under enough pressure to remain metallic. As Earth rotates, convection currents in this liquid outer core generate our magnetic field. That magnetic field deflects solar wind and cosmic radiation, protecting the atmosphere and surface life. Without gravity, sorting materials by density, Earth wouldn't have a liquid iron core. Without that, no magnetic field. Without magnetic field protection, solar wind would strip away our atmosphere over millions of years. Like what happened to Mars. Mars is smaller than Earth, about half the diameter, 1/10 the mass. Smaller planet means weaker gravity. Weaker gravity means it couldn't hold on to lighter atmospheric gases as well. But the real killer was the magnetic field. Mars had a magnetic field once. Evidence shows it died about 4 billion years ago, probably because the planet's small size meant its core cooled faster, solidifying. No liquid core motion, no magnetic dynamo, no protective field. With no magnetic shield, solar wind attacked the atmosphere directly. Over millions of years, it stripped most of the air away. Mars once had rivers, lakes, maybe even an ocean covering much of its northern hemisphere. The evidence is carved into the surface, dry riverbeds, ancient shorelines, minerals that only form in water. Now, a frozen desert, atmospheric pressure less than 1% of Earth's, cold enough that carbon dioxide freezes out of the air in winter, radiation bathing the surface unimpeded, a cautionary tale about what happens when a planet loses its magnetic protection. The moon sculpts Earth in subtler ways. Its gravity creates tides. Twice a day, the oceans rise and fall, not because the moon pulls water toward it exactly, because the moon's mass curves space-time more strongly on Earth's near side than its far side. This differential curvature, tidal force, creates bulges in the ocean. 2 bulges, actually. One on the side facing the moon, one on the opposite side. As Earth rotates through these bulges, coastlines experience high tide, low tide, high tide, low tide. The moon's tidal forces also slow Earth's rotation, very gradually, about 2 milliseconds per century. Doesn't sound like much, but 4 billion years ago, a day on Earth lasted only about 6 hours. The moon has been applying the brakes ever since stealing Earth's rotational energy and converting it into orbital energy, spiraling slowly outward. Next time you're at the beach, waves lapping at your feet, remember, the moon is curving space-time from 384,000 kilometers away, and that curvature is lifting billions of tons of ocean water. Though really the moon isn't pulling anything, just warping geometry. Jupiter deserves special mention. The giant, more massive than all other planets combined, its gravity dominates the outer solar system, keeping things orderly and chaotic. The asteroid belt between Mars and Jupiter contains millions of rocks, but it's not evenly distributed. There are gaps regions almost empty of asteroids. The Kirkwood Gaps, named after Daniel Kirkwood, who noticed them in 1866. These gaps occur at orbital distances, where an asteroid would have a period that's a simple fraction of Jupiter's period, 1/3 Jupiter's period, 1/2, 2/5. At these locations, Jupiter's gravity tugs the asteroid in the same direction, at the same point in its orbit over and over, like pushing someone on a swing at exactly the right moment each time. The repeated kicks gradually push the asteroid into a different orbit, clearing the gap. Orbital resonance, gravity conducting a cosmic symphony. In July 1994, astronomers watched something spectacular. Comet Shoemaker-Levy 9, already broken into 21 fragments by Jupiter's tidal forces on a previous pass, slammed into the giant planet. Fragment after fragment, each impact releasing energy equivalent to millions of nuclear bombs. Dark scars appeared in Jupiter's atmosphere, some larger than Earth, visible for months. Jupiter shields us in a way. Its enormous gravity attracts comets and asteroids that might otherwise hit Earth. It's like having a massive bodyguard in the outer solar system, taking hits meant for us. Thanks, big guy. Saturn's rings show gravity's artistic side. Billions of ice particles orbiting the planet, ranging from dust grains to house-sized chunks. But the rings have structure, gaps, divisions. The most prominent is the Cassini division, a dark band separating the A and B rings. Small moons, shepherd moons, orbit within and near the rings. Their gravity creates waves, clears gaps, keeps particles confined. The rings aren't static. They're constantly sculpted by gravitational interactions, a dynamic system maintained by dozens of moons, some only kilometers across. Gravity creates balance too. In a two-body system, say Earth and Sun, there are 5 special points, called Lagrange points, where gravitational forces and orbital motion balance perfectly. Park a spacecraft there, and it stays put relative to Earth and Sun without needing fuel. The James Webb Space Telescope sits at L2, about 1.5 million kilometers from Earth, on the side away from the Sun. It orbits the Sun at the same rate as Earth, maintaining its position. Clever engineering using gravity's geometry. Jupiter's like the big brother who takes the beatings meant for his younger siblings, absorbing dangerous asteroids and comets. We owe that gas giant our appreciation. But planets are children compared to what comes next. Stars where gravity battles nuclear fire in an epic struggle that forges the elements and lights the cosmos. Stars are born from gravity's patient work. Giant molecular clouds drift through the galaxy, enormous regions of gas and dust, often 100 light-years across, mostly hydrogen, some helium, traces of heavier elements from earlier stellar deaths. These clouds are cold, just 10 or 20 degrees above absolute zero. Tenuous, barely denser than the vacuum of space. But here and there, slight variations in density exist. Maybe a shock wave from a nearby supernova compressed a region. Maybe 2 clouds collided. Doesn't matter. Once a region gets slightly denser than its surroundings, gravity takes over. The dense region pulls in more material from around it. As it contracts, it gets denser, increasing its gravitational pull, attracting even more gas. Positive feedback. The cloud collapses inward, fragmenting into smaller clumps. Each clump contracts independently. As material falls inward, gravitational potential energy converts to heat. The center grows hotter and hotter. Pressure builds. Eventually, could take 1,000,000 years, the core temperature reaches about 10 million degrees Celsius. At that temperature, hydrogen nuclei move fast enough to overcome electromagnetic repulsion and fuse. 4 hydrogen nuclei combine to make 1 helium nucleus, releasing energy. Nuclear fusion ignites. The protostar becomes a star, and here's where the battle begins. Fusion releases tremendous energy, outward pressure pushing against gravity's inward crush. For a stable star, these forces balance. Hydrostatic equilibrium. Fusion pressure equals gravitational pressure. The star shines steadily, converting mass to energy via Einstein's E/mc2. The Sun has maintained this balance for 4.6 billion years. It burns 600 million tons of hydrogen every second, fusing it into 596 million tons of helium. The missing 4 million tons, converted entirely to energy. The sunlight warming your face, powering photosynthesis, driving weather that's mass becoming energy. The sun will continue burning for another 5 billion years, give or take. Then the hydrogen in the core runs out. When that happens, fusion stops. Gravity wins temporarily. The core contracts, but contraction heats it up. Eventually, the core gets hot enough to fuse helium into carbon. Meanwhile, a shell of hydrogen around the core starts fusing. The star swells enormously, becoming a red giant. Our sun's red giant phase will be spectacular and terrifying. It'll expand past Mercury's orbit, past Venus, possibly past Earth. We'll either be swallowed or scorched to a cinder. Either way, not surviving. For massive stars, say 10 times the sun's mass or more, the story gets violent. When core hydrogen runs out, the core contracts and heats until helium fuses. When helium runs out, the core contracts again, heating further, fusing carbon into neon and oxygen. The pattern continues. Neon to oxygen and magnesium, oxygen to silicon and sulfur, silicon to iron. The star becomes an onion of shells, each layer fusing different elements, getting hotter and denser as you go inward. Iron core at the centers, silicon shell around it, oxygen shell, carbon shell, helium shell, hydrogen shell at the surface. But iron is the end of the line. Fusing iron doesn't release energy, it absorbs energy. Once the core is iron, fusion stops. No outward pressure remains. Gravity crushes the core. In about 1/10 of a second, the core collapses from roughly the size of Earth to about 20 kilometers across. Electron pressure can't stop it. Electrons get crushed into protons, forming neutrons. The core becomes a neutron star. The collapse rebounds. A shock wave blasts outward, ripping the star apart. A supernova. For a few weeks, the exploding star outshines its entire galaxy. Billions of stars, and this one dying star is brighter than all of them combined. The explosion scatters heavy elements into space. Carbon, oxygen, silicon, iron, gold, platinum. Everything heavier than helium that exists in the universe came from stellar fusion and supernova explosions. You are literally made of stardust. The carbon forming your DNA forged in the core of a star that exploded billions of years ago. The oxygen you breathe, stellar fusion. The nitrogen in your proteins, stellar fusion. The calcium in your bones, stellar fusion. The iron in your blood carrying oxygen to your cells, created in a star's core in the seconds before it exploded. Every atom in your body, except hydrogen and helium, which came from the Big Bang, was manufactured inside a star. Then, that star died, violently spewing its guts across interstellar space. Those atoms drifted for eons, eventually swept into the cloud that formed our solar system. They became part of Earth, part of the elements that built life, part of you. You're not separate from the cosmos. You're recycled stellar material. The universe made conscious. That gold wedding ring on your finger. Each gold atom was created in the collision of two neutron stars, probably 5 billion years ago, before Earth even existed. Gold is so heavy, so neutron-rich, that it requires the extreme conditions of a neutron star merger to form. On August 17, 2017, LIGO and Virgo detected gravitational waves from exactly such a collision. Telescopes worldwide observed the explosion a kilonova. Spectroscopic analysis confirmed gold, platinum, uranium, all the heaviest elements being synthesized in real time. We finally had proof of where gold comes from. Neutron stars violently embracing creating treasure in their death throes. Betelgeuse, the red supergiant in the constellation Orion, is nearing the end. It's already burned through most of its fuel. Could explode tomorrow. Could explode in 100,000 years. When it does, we'll see a supernova visible in daylight for 6 months, brighter than the full moon. A new star in the sky, marking the violent death of a stellar giant 650 light years away. Early in cosmic history, the first star's population 3 stars formed from gas clouds containing only hydrogen and helium, no heavy elements, no metals in astronomical parlance. These metal-free stars couldn't form rocky planets. Planets require elements like carbon, oxygen, silicon, iron. Without supernovas enriching the interstellar medium with these elements, planetary systems like ours couldn't exist. We're made possible by stellar death. Generations of stars lived fused elements exploded, enriching the galaxy. Only then could Earth form. Only then could life arise. The sun fuses hydrogen via the proton-proton chain. 4 protons become 1 helium nucleus through a series of steps. Larger stars use a different process, the CNO cycle, where carbon, nitrogen, and oxygen act as catalysts. Same result, hydrogen to helium, but different pathway. Temperature determines which process dominates. The sun burns 600 million tons per second and has enough fuel for 5 billion more years. That's like someone eating 20 hamburgers a day, yet somehow living to 90. The efficiency of nuclear fusion is absurd. You need very little fuel to generate enormous energy. But some stars refuse to go quietly. They don't settle for red giant phase or supernova. They collapse beyond neutron stars into something far more terrifying. When a massive star collapses, but isn't quite massive enough to form a black hole, you get something almost as bizarre: a neutron star. Take 1.4 times the sun's mass, about 280,000 times Earth's mass, and compress it into a sphere 20 kilometers across, about 12 miles, roughly the size of Manhattan. The density is incomprehensible, 400,000 trillion times denser than water. A single teaspoon of neutron star material would weigh about 1 billion tons. That's 1,000 Empire State Buildings in a spoonful. If you compressed all of humanity, 8 billion people, into neutron star density, we'd fit in a sugar cube, with room to spare. The surface gravity is 200 billion times Earth's gravity. Drop something from a height of 1 centimeter, less than half an inch, and it hits the surface at 2,000 kilometers per second. That's about 0.7% the speed of light. from 1 centimeter. A human standing on a neutron star's surface. You wouldn't stand, you'd be crushed instantly into a layer of atoms, roughly 1 atom thick, smeared across the surface like paint. Your constituent particles pressed so tightly together that individual atoms cease to exist as separate entities. Light escaping the surface gets gravitationally redshifted by about 30%. Photons climbing out of that intense gravitational well lose energy, shifting toward the red end of the spectrum. The interior is even stranger. Near the surface, you've got a solid crust of iron nuclei packed into a crystalline lattice. Deeper down nuclei merge, forming increasingly neutron-rich isotopes that can't exist anywhere else. Deeper still, nuclei dissolve entirely. You get a neutron superfluid neutrons, flowing with zero viscosity, defying normal physics. At the very center, we're not sure. Maybe neutron degenerate matter, maybe quark-gluon plasma quarks, freed from protons and neutrons existing as a soup. Maybe something even more exotic. We can't reproduce these conditions in any lab. We can only theorize and observe. Some neutron stars rotate fast, incredibly fast. The fastest known pulsar spins 716 times per second, 716 rotations every second. A 20-kilometer sphere spinning so fast that its equator moves at about 24% the speed of light. Why so fast? Conservation of angular momentum. The star was rotating before it collapsed. As it shrank from planet size to city size, it spun faster, like an ice skater pulling in their arms. Except the skater is a stellar corpse spinning at a substantial fraction of light speed. These rotating neutron stars have magnetic fields trillions of times stronger than Earth's. The magnetic axis usually doesn't align with the rotation axis. As the star spins, the magnetic field whips around, accelerating charged particles near the poles. These particles emit beams of radiation, radio waves, X-rays, gamma rays, shooting out from the magnetic poles. If one of those beams points toward Earth, we see a pulse. Then the beam sweeps away. Then it comes back around. Pulse, silence, pulse, silence. A cosmic lighthouse. We call them pulsars. Jocelyn Bell discovered the first pulsar in 1967. She was a graduate student analyzing radio telescope data when she noticed something strange. A signal repeating every 133 seconds. Perfectly regular. Unnaturally regular. Her supervisor, Anthony Hewish, jokingly suggested it might be aliens. They even nicknamed it LGM-1, Little Green Men. 1. Imagine that tension. A graduate student potentially discovering the first evidence of extraterrestrial intelligence. But as they found more pulsars with different periods, the alien hypothesis collapsed. These were natural phenomena, rotating neutron stars, nature's most precise clocks ticking with regularity, better than atomic clocks in many cases. Pulsars have practical applications. Future spacecraft might navigate using pulsar timing, cosmic GPS. Each pulsar has a unique signature, a specific period. By measuring the arrival times of pulses from multiple pulsars, you can triangulate your position in three-dimensional space. NASA included a pulsar map on the Voyager Golden Record, showing Earth's location relative to 14 pulsars. If aliens find it, they can figure out where we are. Pulsars also test general relativity with extreme precision. The Hulse-Taylor binary pulsar, two neutron stars orbiting each other, has been monitored since 1974. The orbit is decaying exactly as predicted by gravitational wave emission. Watching this system is like watching general relativity's math play out in real time. Some neutron stars have magnetic fields even stronger than normal pulsars, magnetars. These objects have fields so intense they can warp the vacuum itself, creating bizarre quantum effects. A magnetar's field is strong enough to erase your credit card from 1,000 kilometers away. If one existed within 1,000 kilometers of Earth, it would strip the iron from your hemoglobin. August 2017 brought spectacular confirmation of neutron star collision dynamics. LIGO and Virgo detected gravitational waves from two neutron stars spiraling together and merging. The kilonova explosion that followed created heavy elements, gold, platinum, uranium. We watched in real time the cosmic factory producing precious metals. Some physicists speculate that neutron star interiors might contain quark stars regions where matter breaks down into quark soup rather than remaining in a neutron form. We won't know without better observations or theoretical breakthroughs. Pulsars occasionally experience glitches, sudden spin-ups, where they rotate faster for a while, probably caused by the rigid crust, cracking and rearranging, transferring angular momentum from the superfluid interior to the surface, like tectonic earthquakes, but on a neutron star spinning hundreds of times per second. Picture all of Manhattan buildings, streets, millions of people compressed into a marble. Now spin that marble 700 times every second. Now give it a magnetic field 1,000,000,000,000 times Earth's. The universe doesn't do gentle. If you weigh 180 pounds on Earth, you'd weigh 36 trillion tons on a neutron star. Finally, a legitimate excuse for not losing weight. If you're still reading, your brain clearly enjoys being pushed to its limits. Good news, the worst is yet to come, because neutron stars are only level 2 weirdness. Level 3 black holes is where time dies and space curves to infinity. The event horizon isn't a surface, not a barrier you can touch, not a wall or membrane. It's a boundary in space-time, a point of no return defined purely by geometry. Cross it, and every possible future path leads inward. Not because something pulls you, because the curvature of space-time itself makes escape impossible. Your future points toward the singularity, as surely as your future in normal space-time points forward in time. You can no more avoid the singularity than you can avoid tomorrow. The event horizon's size depends entirely on mass. For any given mass, there's a critical radius, the Schwarzschild radius, where escape velocity equals light speed. Inside that radius, not even light escapes. Compress Earth into a black hole. You'd need to squeeze it down to about 9 millimeters, less than half an inch. The entire planet, all 6 × 10^124 kilograms, packed into a marble-sized sphere. The Sun Schwarzschild radius of about 3 kilometers, roughly 2 miles. A black hole 10 times the Sun's mass, 30 kilometers across. A supermassive black hole with a billion solar masses like those at galaxy centers. The event horizon would be larger than Saturn's orbit, nearly 3 billion kilometers across. Think about that. A hole bigger than our entire inner solar system. Here's where things get truly mind-bending. Time behaves completely differently depending on who's watching. Your perspective falling in, you cross the event horizon in finite time. Minutes maybe. Depends on the black hole's mass. You pass through. Nothing special marks the moment. No sign reading, "Welcome to your doom." No sensation, just continued falling. The horizon isn't locally detectable. Only after you've crossed do you realize all your possible futures lead inward, your friend's perspective watching from a safe distance. You never cross, ever. As you approach the horizon, time dilation becomes extreme. From their viewpoint, your clock slows. Your movements become glacial, asymptotically approaching zero speed at the horizon. They watch you freeze, slow down and slow down and slow down, never quite reaching the boundary. Light from you gets increasingly redshifted, visible light shifting to infrared, then radio waves. You dim, fade, eventually become so redshifted and dim that you disappear from view entirely. But from their perspective, you're still there, frozen at the horizon forever, a ghost image that never quite crosses. Both perspectives are correct. General relativity allows this. There's no universal, now, coordinating events. You experience crossing. They never see you cross. Both true simultaneously. Inside the horizon, space-time is so warped that inward becomes the future direction. The singularity isn't a place you can avoid by moving sideways. It's a moment in your future that you will inevitably reach. Like you can't avoid Thursday by walking east, you can't avoid the singularity by moving in any spatial direction. It's temporally ahead of you, not spatially. This creates the information paradox. Quantum mechanics says information can't be destroyed. It can be scrambled, hidden, made practically irretrievable, but fundamentally it must persist. Yet general relativity says anything crossing the event horizon is lost forever. The information is destroyed. Stephen Hawking originally argued information genuinely gets destroyed, that black holes were the one exception where quantum mechanics fails. This caused uproar, decades of arguments. Finally, in 2004, Hawking conceded he was probably wrong. Current thinking suggests information might be preserved holographically. The holographic principle proposes that all information about a volume of space can be encoded on its boundary. For a black hole, the event horizon acts as that boundary. Information about everything that fell in might be encoded in subtle quantum correlations at the horizon, then gradually released as the black hole evaporates via Hawking radiation. But we don't fully understand the mechanism. Quantum gravity, the theory unifying quantum mechanics and general relativity, would explain it. We don't have that theory yet. Rotating black holes add another layer of weirdness. Most black holes rotate formed from collapsing stars that were spinning. A rotating black hole drags space-time around with it, frame dragging taken to the extreme. Around a rotating black hole is a region called the ergosphere. Inside the ergosphere, space-time is dragged so violently that nothing can remain stationary. You must move with the rotation. You can still escape the ergosphere. It's outside the event horizon, but you can't stand still. Space-time itself is flowing like a river, carrying everything with it. Roger Penrose proposed a process for extracting energy from rotating black holes. The Penrose process. Drop an object into the ergosphere. It splits into two pieces. One piece falls into the black hole, carrying negative energy from the black hole's perspective. The other piece escapes with more energy than the original object had. You've stolen rotational energy from the black hole, slowing its spin. In principle, advanced civilizations could power themselves by extracting energy from rotating black holes. In practice, good luck engineering that. Some solutions to Einstein's equations allow white holes hypothetical time-reversed black holes. Matter can exit, but not enter. Possibly the exit of a black hole connected through a wormhole to another universe. Pure speculation, never observed, probably impossible due to stability issues, but mathematically permissible. Falling into a black hole is like falling in love. Easy to get in, impossible to escape. At least black holes have math explaining them. Want to live a few extra hours? Orbit close to a black hole. Time dilation will slow your aging. Unfortunately, everyone you know will grow old and die while you're gone. Not the best trade-off. And now, the question that should terrify you: what's already fallen into the black hole at the center of our own galaxy, 26,000 light years from Earth? Hidden behind thick clouds of dust and gas lurks the heart of the Milky Way. For most of history, we couldn't see it. Visible light gets absorbed by interstellar dust. The galactic center remained shrouded in mystery, but radio waves pass through dust almost unimpeded. In the 1970s, radio telescopes detected a powerful source at the galaxy's center, Sagittarius Egdo, pronounced Sagittarius A star, a compact radio source, clearly massive, clearly strange. By the 1990s, astronomers began tracking individual stars orbiting this invisible object using infrared telescopes. Infrared also penetrates dust. They mapped the motions of stars near the galactic center with exquisite precision. What they found was shocking. Stars moving absurdly fast in tight orbits around nothing visible, or more accurately around something incredibly massive, packed into an incredibly small volume. Star S2 became the poster child. It orbits Sagittarius A every 16 years. At closest approach, it reaches 7,650 kilometers per second. That's 2.5% the speed of light. An entire star, many times more massive than our sun, whipping around at a substantial fraction of light speed. Only one thing can create such intense gravity in such a small region: a supermassive black hole. 20 years of observations nailed down the mass. 4 million solar masses, 4 million times the mass of our sun, packed into a region smaller than Mercury's orbit. The Schwarzschild radius, the event horizon, is about 12 million kilometers. For comparison, the sun's radius is 700,000 kilometers. This black hole's event horizon is about 17 times the sun's size, but contains 4 million times the mass. In April 2019, the Event Horizon Telescope, a planet-sized network of synchronized radio telescopes, released the first image of Sagittarius A's shadow. Actually, they released the image of M87 Esprit, first a supermassive black hole 55 million light years away, because it was easier to image. Sagittarius A's came later because it's so variable, changing on timescales of minutes. The image shows exactly what Einstein's equations predict: a dark central region, the black hole's shadow, surrounded by a bright ring of glowing gas. The shadow is about twice the size of the event horizon, created by light bending around the black hole before escaping. Perfect match. 104 years after Einstein published general relativity, we photographed the shadow cast by a black hole, and it looked precisely as predicted. What does Sagittarius AA eat? Occasionally a star wanders too close. Tidal forces rip it apart, spaghettification on a stellar scale. The star's gas forms an accretion disk spiraling inward, heating to millions of degrees, glowing in X-rays, before crossing the event horizon and vanishing forever. Right now, Sagittarius A is on a diet, relatively quiet, not actively feeding on much material. But sometimes it flares sudden increases in brightness. The black hole brightens by a factor of 100 or more in just a few hours, then dims again, probably caused by clumps of gas or asteroids falling and heating as they spiral toward doom. There's a gas cloud G2 that's been monitored for years. It came close to Sagittarius A. In 2014, some astronomers thought it might get shredded and consumed, triggering a spectacular light show. Didn't happen. G2 survived, probably because it had a star embedded in it, holding it together against tidal forces. Disappointing for drama, but scientifically interesting. If a star actually falls into Sagittarius A, we'd see an incredible display. Years of brightening as the star spirals in, getting torn apart, forming an accretion disk, heating, radiating. Then at the event horizon, the light would redshift away to nothing. The star would vanish its mass, added to the black hole, and the universe would never know what happened inside. Every large galaxy has a supermassive black hole at its center. Bigger galaxy, bigger black hole. There's a relationship. The black hole mass correlates with the galaxy's bulge mass. Why, we don't fully know. Somehow black holes and galaxies co-evolve. Right now you're orbiting Sagittarius A. All of us are. The Sun, Earth, everything in the solar system follows a roughly circular orbit around the galactic center. It takes about 225 million years to complete one orbit. The last time we were at this point in our galactic orbit, dinosaurs were just beginning to evolve. Next time around, who knows what'll be here. In 2020, astronomers discovered star S474, which reaches speeds of 8%, the speed of light 24,000 kilometers per second at closest approach to Sagittarius AI. That's the fastest star we know, pushed to relativistic speeds by the black hole's immense gravity. There might be a second black hole in the Milky Way, not as massive as Sagittarius A, but substantial, possibly hundreds or thousands of solar masses lurking somewhere in the galaxy. Intermediate mass black holes are rare and hard to find. We're searching. In 2024, astronomers released the first movie of Sagittarius A, so not just a single image, but footage showing matter moving around the black hole over time, watching space-time dynamics play out, seeing gas orbit heat fall in, general relativity in motion. Sagittarius A weighs 4 million times the Sun, but fits inside Mercury's orbit, like stuffing 4 million Arnold Schwarzeneggers into a refrigerator. Extremely tight packing. You've seen black holes devour stars. Now let's watch galaxies devour galaxies. We've mapped galaxies across billions of light years, measured their light output, counted their stars, calculated their mass based on visible matter. Then we watch them rotate. And something's wrong. Galaxies spin too fast. Way too fast. Based on the stars and gas, we can see outer regions should be moving slower. Orbital velocity should decrease with distance from the galactic center, just like planets farther from the Sun move slower. But they don't. Stars at a galaxy's edge move just as fast as stars closer in, sometimes faster. The rotation curve stays flat instead of dropping off. This violates everything we know. Unless there's additional mass we can't see, a lot of additional mass, surrounding each galaxy in a massive halo, providing extra gravitational pull, keeping those outer stars moving fast. We call it dark matter. Dark because it doesn't emit, absorb, or reflect light, doesn't interact electromagnetically at all. We only know it exists because of gravity. Its mass curves spacetime. We see that curvature's effects on visible matter and on light passing through. Gravitational lensing provides dramatic evidence. When light from a distant galaxy passes near a massive galaxy cluster, the cluster's gravity bends the light. We see multiple distorted images of the background galaxy. Arcs rings sometimes complete Einstein crosses. By mapping these distortions, we can calculate the cluster's total mass. And here's the thing, the visible matter star's gas. Everything we can see accounts for only about 15% of the total mass needed to create the observed lensing. The other 85% dark matter, invisible, undetectable, except through gravity. The bullet cluster provides the smoking gun. Two galaxy clusters collided at millions of kilometers per hour. The normal matter, hot gas, interacted and slowed down, compressed in the collision zone. But dark matter doesn't interact. It passed right through. Gravitational lensing shows most of the mass is now separated from the visible gas. Dark matter and normal matter behaved differently in the collision, proving dark matter isn't just regular matter that happens to be dark. So, what is it? We don't know. Seriously, 27% of the universe's mass energy, and we have no idea what it's made of. Leading candidates include WIMPs, weakly interacting massive particles, hypothetical particles that barely interact with normal matter, except through gravity and possibly the weak nuclear force. They'd pass through you constantly, billions per second, and you'd never notice. Axions are another possibility. Hypothetical particles proposed to solve a problem in quantum chromodynamics. If they exist and have the right properties, they could be dark matter, light numerous, forming a vast invisible sea permeating the universe. Or maybe dark matter is primordial, black holes, tiny black holes formed in the early universe, not from stellar collapse. These would be gravitationally detectable, but otherwise invisible. Recent observations have made this less likely for most dark matter, but it might explain some fraction. The truth, we're fishing in the dark. Literally. Experiments to detect dark matter directly have been running for decades. The Elux Zeppelin experiment, a mile underground in an old gold mine in South Dakota, uses 7 tons of liquid xenon to catch the incredibly rare interactions between dark matter particles and normal matter. It's surrounded by layers of shielding to block cosmic rays and other background radiation. So far, nothing definitive. A few candidate events, but nothing conclusive. Dark matter remains frustratingly elusive. Right now, billions of dark matter particles are passing through your body every second, through Earth, through the sun, through everything. They barely notice normal matter exists, like ghosts drifting through walls, except real and comprising most of the universe's mass. It's like being a fish in water. Fish don't see water. They swim through it constantly, but it's so omnipresent, so all-encompassing that it's invisible to them. We're swimming in dark matter, oblivious to its presence, except for the gravitational ripples it creates. Some physicists propose dark matter might be its own exotic particle zoo. Maybe there's dark electromagnetism, dark atoms, dark chemistry, an entire shadow sector of physics running parallel to ours, interacting only through gravity. Pure speculation, but intriguing. The distribution of dark matter shapes cosmic structure. Computer simulations show that dark matter formed the scaffolding upon which galaxies assembled. In the early universe, slight overdensities in dark matter gravitationally attracted normal matter. stars, and galaxies formed in the densest regions of the dark matter web. Without dark matter, galaxies, as we know them, couldn't exist. You exist because of dark matter. The Milky Way formed in a dark matter halo. That halo's gravity holds our galaxy together. Without it, the stars would fly apart. Earth wouldn't exist. You wouldn't exist. Dark matter takes up 27% of the universe, but remains invisible. Like taxes, always there, always affecting you, but you never actually see it. Just notice its effects when you check your bank account, or in this case, galaxy rotation curves. Here's what we know for certain. Dark matter exists. It's gravitationally active. It doesn't interact electromagnetically, and it's everywhere. What we don't know, what it's made of, how it formed, whether it has any internal structure, or how to detect it directly. This is one of the greatest mysteries in physics. We've identified a major component of the universe and have essentially no idea what it is. Imagine if 27% of your house was invisible. You'd know it was there. Your floor plan wouldn't make sense otherwise, but you couldn't see it, couldn't touch it, couldn't interact with it, except by walking around the space it occupies. That's our universe. Most of what exists is hidden from us. And the other 68%, that's even more insane. In 1998, two teams of astronomers studying distant supernovas made a discovery that changed everything. They were measuring how fast the universe's expansion was slowing down. Everyone assumed it was slowing. Gravity from all the matter in the universe should be pulling everything back together, decelerating the expansion. The data said otherwise. The universe's expansion isn't slowing down. It's speeding up, accelerating. Distant supernovas were dimmer than expected, meaning they were farther away than they should be if expansion were decelerating. Something is pushing space apart, counteracting gravity, causing expansion to accelerate. The teams published their results. The astronomy community went into shock. This made no sense. It violated intuition, violated expectations, violated what everyone thought they knew about cosmology. But the evidence was solid. Multiple independent measurements confirmed it. The universe is accelerating. Whatever causes this acceleration, we call it dark energy, and it dominates everything. Dark energy makes up approximately 68% of the universe's total mass energy. 68%, more than twice as much as dark matter, nearly 14 times more than normal matter. What is dark energy? We have no idea. None. It's the most honest answer science can give. We've identified this component through its effects, but we don't understand its nature. One possibility, dark energy, is the cosmological constant, a property of space itself. Empty space might have inherent energy density. As the universe expands, creating more space, there's more dark energy. This positive feedback drives accelerating expansion. Einstein originally proposed a cosmological constant in 1917 for completely different reasons. He wanted a static universe, so he added this term to his equations to balance gravity. When Hubble discovered the universe was expanding, Einstein supposedly called the cosmological constant his biggest blunder. Turns out he was right the first time, just for the wrong reasons. Another possibility, dark energy, is a dynamic field, something that changes over time. Quintessence, as some call it. A scalar field permeating space with negative pressure. Unlike the cosmological constant quintessence, could vary in strength and density as the universe evolves. Or maybe it's phantom energy, a more exotic form with even stranger properties. Phantom energy would increase in density as the universe expands, eventually becoming so strong it tears space-time apart. The Big Rip scenario. First galaxy clusters unbind, then galaxies themselves, solar systems, planets, molecules, atoms. Eventually, about 22 billion years from now, in this scenario, space-time itself shreds, everything ripped apart by exponentially accelerating expansion. Speculative, absolutely, but consistent with some observational data. We can't rule it out yet. The acceleration has profound implications. Galaxies beyond our local gravitationally bound group are being carried away faster and faster. Eventually, they'll recede so quickly that light from them can no longer reach us. They'll pass beyond our cosmic horizon. In about 100 billion years, observers in the Milky Way will look out and see only our local cluster of gravitationally bound galaxies. Everything else will have disappeared beyond the observable universe. The cosmic microwave background will have redshifted beyond detection. Future astronomers will have no evidence the universe ever expanded, no evidence of the Big Bang, no way to discover cosmology as we know it. They'll be prisoners of their era, cosmologically blind, unable to see the broader truth. We're fortunate to exist when we can still observe the universe's history, written in distant light. It's like standing on an accelerating conveyor belt. Everything around you slides away faster and faster. Nearby objects you can grab and hold on to, but things farther away accelerate beyond reach. Eventually, everything beyond arm's length vanishes over the horizon. You're left isolated, watching your observable world shrink. Dark energy might not be constant. Some measurements hint it might be changing, over time getting stronger or weaker. If it's changing, that rules out the cosmological constant and points towards something more dynamic. But the data isn't conclusive yet. We need better observations. The universe is 95% mystery. Dark matter, 27%. Dark energy, 68%. Normal matter, stars, planets, gas dust, everything made of atoms, everything we can directly observe, just 5%. It's like NASA bought a house but can only see 5% of the rooms. The other 95% exists, affects the house's structure, determines its behavior, but remains completely hidden. We deduce their existence from how the visible parts behave, but we can't open the doors. If you're feeling dizzy right now, congratulations. You're responding appropriately. Science is dizzy too. We've discovered that we don't understand most of the universe. We've quantified our ignorance with precision: 27% dark matter, 68% dark energy. But that doesn't make it less frustrating. Some physicists wonder if dark energy indicates general relativity breaks down on cosmic scales. Maybe gravity behaves differently across billions of light years. Modified gravity theories attempt to explain observations without invoking dark energy. So far, none work as well as dark energy models, but the search continues. The James Webb Space Telescope is collecting data that might help, measuring distant supernovas with unprecedented precision, mapping the universe's expansion history in detail. Maybe we'll find hints about dark energy's nature. Maybe we'll discover it's changing over time. Maybe we'll find something completely unexpected. The future of the universe depends on dark energy. If its constant expansion accelerates, forever leading to heat death. If it's getting stronger, the Big Rip might tear everything apart. If it's getting weaker, expansion might eventually reverse, leading to a big crunch. We don't know. We're watching the universe's fate play out, but we don't understand the script. But humanity doesn't give up. We never have. When faced with mysteries, we build better instruments, design cleverer experiments, think harder. We've come this far. We'll go further. LIGO detected gravitational waves in 2015. Since then, dozens more detections. Black hole mergers, neutron star collisions, each event teaching us something new about extreme gravity, dense matter, the universe's violent side. But LIGO is just the beginning. Upgrades are coming. LIGO A+, with better lasers, improved mirrors, more sensitive detectors. It'll see 3 times farther into space, detecting triple the volume, finding far more events, more black holes merging, more neutron stars colliding, more tests of general relativity in extreme conditions. And in the 2030s, LISA, the Laser Interferometer Space Antenna, launches. 3 spacecraft arranged in a triangle with sides 5 million kilometers long orbiting the Sun. LISA will detect lower frequency gravitational waves that LIGO can't see, waves from supermassive black holes merging at galaxy centers. These events take years to complete, producing waves far below LIGO's sensitivity range. LISA will hear the universe's deep bass notes. LIGO hears the high-pitched chirps of stellar mass black holes. Together, they'll create a gravitational wave symphony spanning the cosmic frequency spectrum. When 2 galaxies merge, their central supermassive black holes eventually spiral together. The final coalescence, 2 black holes, each millions or billions of solar masses, merging into one, releases gravitational wave energy equivalent to the light output of every star in the observable universe. For that brief moment, the gravitational wave power exceeds all electromagnetic radiation in the cosmos. LISA will detect these events across the universe. We'll catalog supermassive black hole mergers measuring their masses, spins, distances. We'll watch cosmic structure assemble in real time through gravitational waves. The event horizon, telescope-imaged black hole shadows, static images, beautiful groundbreaking but frozen moments. The next generation will produce movies, real-time video of matter spiraling into black holes, gas clouds orbiting, heating, falling through the event horizon and vanishing. Your grandchildren will watch black hole videos on whatever replaces YouTube, seeing matter cross event horizons, watching space-time dynamics play out. Like you watch documentaries today, they'll casually observe the most extreme phenomena in the universe. Scientists are searching for primordial gravitational waves, ripples from the Big Bang's first moments. If cosmic inflation happened, exponential expansion in the universe's first fraction of a second, it would have generated gravitational waves. These waves would have left distinctive patterns in the cosmic microwave background radiation. Finding them would confirm inflation, reveal the energy scale of the early universe, and point toward quantum gravity. It would be like having a telescope that sees back to 10 hours or 35 seconds after the Big Bang, when the universe was unimaginably tiny, hot, and dense, earlier than any electromagnetic observation can reach. Experiments like BICEP and the upcoming LightBird satellite are searching. So far, no confirmed detection. But the search continues. If primordial gravitational waves exist, we'll find them. Quantum gravity remains the holy grail. unifying general relativity and quantum mechanics, describing what happens inside black holes at the Big Bang's first instant at the Planck scale, where space-time itself might become quantized. String theory, loop quantum gravity, causal set theory, asymptotic safety, multiple approaches, none yet confirmed. The theory might be just beyond our current mathematical reach, or we might need experimental guidance, some observation that points us in the right direction. Particle colliders can't reach the energies where quantum gravity matters. Those energies are 10 to the power 16 times higher than the Large Hadron Collider. We'll never build an accelerator that powerful, but we might detect quantum gravity's subtle effects in precision experiments, tiny deviations from general relativity, unusual behavior in extreme environments. Or maybe quantum gravity will remain theoretical for centuries, a beautiful mathematical framework we construct but can't test. Though that seems unlikely, nature usually cooperates eventually. We just need patience and cleverness. The Alcubierre drive, proposed by physicist Miguel Alcubierre in 1994, offers a theoretical way to travel faster than light without violating relativity. You don't move through space faster than light. Instead, you contract space in front of your ship and expand it behind, a warp bubble carrying you along. The space moves. You're stationary within it. The math works. Solutions to Einstein's equations permit this. And it's a huge, but it requires exotic matter with negative energy density, something that gravitationally repels rather than attracts. We've never seen such matter. It might not exist, or it might be impossible to produce in sufficient quantities. So beautiful theory, practical reality, good luck with that. Gravitational waves might enable interstellar communication. Light gets absorbed by dust and gas. Radio waves get distorted by plasma. But gravitational waves pass through matter almost completely unimpeded. Modulate them correctly, and you could send messages across the galaxy that nothing can block. Of course, generating detectable gravitational waves requires accelerating enormous masses at ridiculous speeds. Current technology is nowhere close. But an advanced civilization, maybe. If LIGO detects artificial gravitational waves, someday a clearly modulated signal, not from a natural source, will know we're not alone. Researchers are exploring space-time crystals, materials with patterns that repeat not just in space, but in time, quantum systems that oscillate in their ground state, perpetually moving without energy input, weird quantum effects made tangible. Could we engineer space-time itself, create regions with different properties? Probably not with current physics, but future understanding might allow space-time engineering, artificial gravity, controlled wormholes, manipulated dimensionality, pure speculation, but based on mathematical possibilities within general relativity. The next century will bring wonders we can't imagine, like trying to explain smartphones to someone from 1920. The concepts don't translate. The technology seems like magic, but the biggest discovery won't be technology. It'll be something more profound. Albert Einstein once said, "The most incomprehensible thing about the universe is that it's comprehensible." Think about that. Really think about it. We're hairless apes, descended from tree-dwelling primates. Our ancestors spent millions of years worrying about finding food, avoiding predators, and reproducing. Natural selection didn't optimize our brains for understanding black holes or curved space-time. It optimized them for throwing spears recognizing faces, and navigating social hierarchies. Yet here we are, understanding the universe across 93 billion light years, measuring gravitational waves from events 1.3 billion years ago, photographing black holes at galaxy centers millions of light years distant, calculating the curvature of space-time to extraordinary precision. We've figured out fundamental laws governing reality, from the subatomic to the cosmic. We've traced the universe's history back to fractions of a second after the Big Bang. We've predicted phenomena, gravitational waves, time dilation, black holes, and then found them exactly where the math said they'd be. This shouldn't work. By all rights, the universe should be incomprehensible to creatures like us. We should be stuck understanding only our immediate environment, the things relevant to survival and reproduction. Instead, we can grasp quantum mechanics, general relativity, the expansion of space-time itself. Why, nobody knows. It's one of the deepest mysteries. The universe appears to be mathematically structured in a way our minds can decode. The same patterns that govern falling apples govern orbiting galaxies. The same geometry that describes curved surfaces describes curved space-time. Nature seems to run on mathematics we can understand. You are made of stardust, not poetically, literally, factually, scientifically. Every atom in your body, heavier than helium, carbon, nitrogen, oxygen, phosphorus, sulfur, calcium, iron, was forged in stellar cores through nuclear fusion. Then those stars died, many in violent supernova explosions, scattering their synthesized elements across space. The carbon forming the backbone of your DNA, created in a star's core billions of years ago. The oxygen you're breathing right now, stellar fusion. The calcium in your bones, stellar fusion. The iron in your hemoglobin, carrying oxygen through your bloodstream, created in a star's final seconds before it exploded. Those atoms drifted through space for eons, eventually swept into the molecular cloud that collapsed to form our solar system. They became part of Earth, part of the minerals and compounds that eventually assembled into the first living cells. Through billions of years of evolution, those stellar atoms arranged themselves into increasingly complex forms, into fish, into amphibians, into mammals, into primates, into you. You're not separate from the cosmos. You're a temporary arrangement of recycled stellar material. The universe has organized a small portion of itself into a form capable of contemplating its own existence. Think about that. You are the universe experiencing itself, cosmic matter that has become conscious, stardust that wonders about stars. Every thought in your head, every emotion you feel, every memory you cherish, it's all atoms from dead stars interacting according to the laws of physics. You are physics made flesh, mathematics made conscious, the universe's way of knowing itself. Carl Sagan said it beautifully. We are a way for the cosmos to know itself. Not metaphor, not inspiration. Statement of fact. The universe existed for 13.8 billion years without awareness. Hydrogen fused in stars. Galaxies formed and evolved. Black holes devoured matter. But nothing knew it was happening. No consciousness observed it. No mind comprehended it. Then, on at least one small planet orbiting an ordinary star in an unremarkable galaxy, chemistry became complex enough to generate awareness. Neurons firing in patterns that create thought. Consciousness emerging from matter. And suddenly, for the first time, the universe could look at itself, could measure itself, could understand itself. You are that awareness. You are the universe's eyes and mind. Every time you look up at the night sky, the universe is looking at itself. Every time you learn something about physics or astronomy, the universe is learning about itself. You're not a passive observer standing outside reality. You're an integral part of it, active, essential, the cosmos examining its own structure. This brings us to something physicists call the anthropic principle, a controversial but fascinating observation. The universe's fundamental constants appear fine-tuned for life. The gravitational constant, the electromagnetic force strength, the mass of the electron, the cosmological constant, dozens of physical parameters that determine how the universe works. If any of them were even slightly different, life as we know it couldn't exist. If gravity were 0.01% stronger, stars would burn out too quickly for life to evolve. If it were 0.01%, weaker stars wouldn't form at all. No stars, no heavy elements, no planets, no life. If the electromagnetic force were slightly stronger, electrons wouldn't bond into molecules. If slightly weaker atoms couldn't hold together. If the cosmological constant dark energy were much larger, the universe would have expanded too fast for galaxies to form. If it were much smaller, the universe would have collapsed before life could arise. The list goes on, parameter after parameter, precisely balanced. The universe seems calibrated for consciousness. Why 3 possibilities? 1 pure luck. We rolled the cosmic dice and got a universe that supports life. Unlikely, but possible. Given infinite chances, even the improbable becomes inevitable. 2 multiple universes. The multiverse hypothesis. Perhaps countless universes exist, each with a different physical constants. Most are sterile, no stars, no planets, no life. But we necessarily find ourselves in one of the rare universes where the constants allow consciousness. Selection bias. We couldn't exist in the others to observe them. 3. Something deeper. We don't understand yet. Maybe the constants aren't random. Maybe they're determined by principles we haven't discovered. Maybe consciousness plays a fundamental role in the universe's structure through quantum mechanics. Speculative, but not impossible. We don't know which explanation is correct. Maybe none of them. But the fact remains the universe's laws seem remarkably suited for generating complexity, structure, and eventually consciousness. It's like the universe played poker and drew a royal flush. Every card had to be exactly right. 1 card different, and no stars, no planets, no you. Instead, everything aligned perfectly. Gravity strong enough to pull matter together, but weak enough to allow structure. Electromagnetism balanced to permit chemistry. Nuclear forces calibrated to enable fusion and element formation. Dark energy mild enough to allow galaxy formation, but strong enough to prevent eventual collapse. The odds of this happening by chance astronomically small. And yet here we are. The universe's way of beating impossible odds. Some find this comforting. The universe seems to want to create life, create consciousness, create understanding. Others find it unsettling. Are we really just lucky? Or is there something more going on? Einstein spent his later years searching for a unified theory, convinced the universe must make sense as a coherent whole. He never found it. We're still searching. String theory loop. quantum gravity, other approaches, all attempting to show that the universe's seemingly arbitrary constants are actually necessary consequences of deeper principles. Maybe we'll succeed. Maybe we'll discover that consciousness isn't an accident, but an inevitable outcome of physical law, that the universe must eventually examine itself. Or maybe we're alone, a freak occurrence in an infinite cosmos, one brief flash of awareness in the eternal darkness. Either way, you're here, against impossible odds, a thinking, feeling, understanding arrangement of matter that shouldn't exist but does. And now, the final message. Let's bring this home. Gravity isn't a force, it's the curvature of space-time, not a pulling influence reaching across space, but the geometry of reality itself, warped by mass and energy. You're not standing still on flat ground with gravity pulling you down. You're accelerating upward through curved four-dimensional spacetime, held aloft by electromagnetic forces from the ground. Those forces, the atoms in the floor, resisting compression, push against your feet with 150 to 220 pounds of force. That sensation you call weight, that's electromagnetic forces preventing you from following your natural geodesic, the straightest possible path through curved spacetime. Remove the floor, and you'd fall freely, following that geodesic, weightless, experiencing your natural state of motion. The moon orbits Earth, not because Earth's gravity pulls it, because Earth curves spacetime around it, and the moon follows a geodesic through that curved geometry. It's falling endlessly, forever missing Earth, because it's also moving sideways at just the right speed. Earth orbits the Sun for the same reason. The Sun curves spacetime. Earth follows a geodesic, an endless freefall that looks like an orbit from our perspective. The Sun orbits the galactic center, following spacetime curved by 4 million solar masses of black hole, plus hundreds of billions of stars. One orbit every 225 million years. The Milky Way falls toward the Virgo cluster, pulled by the combined mass of thousands of galaxies. And Virgo falls toward the Great Attractor, and everything moves with the expansion of space itself, carried along on the stretching fabric of the universe. You're part of this cosmic dance, every moment moving through four-dimensional spacetime, following geodesics, experiencing geometry. Every atom in your body is older than Earth, forged in stellar cores, scattered in supernova explosions, drifting through space, eventually swept into the cloud that formed our solar system. They've been cycling through the cosmos for billions of years. Now they're part of you, temporarily. When you die, those atoms will return to the universe. Maybe they'll become part of a tree, maybe ocean water, maybe billions of years from now, part of another living thing on another planet. You're not separate from the universe. You're a pattern the universe has formed, a temporary arrangement of matter and energy, conscious and aware, capable of understanding the very laws that govern your existence. This knowledge won't make you rich, won't pay your mortgage, won't solve your daily problems, but it makes you free, free from the illusion that you're just a passive observer. You're an active participant, a crucial part of the cosmic story, free from the misconception that you're insignificant. You're the universe's way of experiencing itself. 13.8 billion years of cosmic evolution produced eyes capable of looking back at the Big Bang, minds capable of understanding black holes, Consciousness capable of grasping curved space-time, free from the fear that nothing matters. Everything matters. You matter. Your existence, improbable, brief, precious, represents the universe achieving self-awareness. You're not standing still. You're moving. Right now. Spinning with Earth's rotation at 1,600 kilometers per hour at the equator, orbiting the Sun at 107,000 kilometers per hour, orbiting the galactic center at 8 to 28,000 kilometers per hour, falling toward Virgo at over 600 kilometers per hour, carried along by cosmic expansion at speeds that dwarf all the rest. Every second, you travel thousands of kilometers through space. Every moment, you slide along your geodesic through space-time. Next time you look at the moon, remember it's falling around Earth endlessly, and you're standing on a rock that's falling around the sun in a galaxy that's falling toward mysteries we're still unraveling. Next time you feel weight, remember that's not gravity pulling you down. That's the ground pushing you up, preventing you from following your natural path through curved space-time. Next time someone tells you to be realistic, tell them, I'm surfing curved space-time at 600 kilometers per second. What are you doing? In 2024, physicists made breakthroughs in quantum gravity research, new experiments linking quantum entanglement with space-time geometry, hints that space and time might emerge from deeper quantum relationships. We're closing in on the unified theory Einstein sought. Future generations will know things we can't imagine. They'll have theories we can't conceive, technology we'd consider magic. They'll look back at our understanding the way we look back at Newton, correct in its domain, but incomplete. They'll detect primordial gravitational waves from the Big Bang. They'll map quantum spacetime structure. They'll possibly engineer spacetime itself, creating controlled wormholes or artificial gravity. They'll expand human understanding in ways we can't predict. But one thing won't change: the sense of wonder, the awe at understanding, the profound recognition that consciousness can grasp the cosmos, that feeling looking up at stars and comprehending what you're seeing that's eternal. Every generation of scientists, every person who learns physics, experiences that same amazement. The universe revealing itself to itself. Your great-great-grandchildren will watch black hole videos the way you watch cat videos on YouTube. Casually, routinely, they'll grow up in a world where gravitational wave astronomy is standard, where quantum gravity is understood, where the mysteries we struggle with are solved and new mysteries have taken their place. But they'll feel the same wonder you can feel right now, understanding that gravity is geometry, that space-time curves, that consciousness emerged from stellar ashes, that the universe is knowable, knowledge accumulates, wonder endures. Now you know you're not being pulled down by gravity. You're being pushed up by electromagnetic forces, resisting your natural tendency to follow a geodesic through curved space-time. Next time you're late for a meeting, blame it on fighting your natural geodesic. Sorry, I'm late. I was resisting the curvature of space-time. Couldn't be helped. Here's the final message, the most important one, the truth you should carry with you. The universe is 93 billion light-years across, contains 2 trillion galaxies, a billion trillion stars, more planets than we can count, black holes, neutron stars, pulsars, quasars, wonders beyond imagination. But there's only one you, One unique arrangement of matter that thinks your thoughts feels your feelings, experiences your life. One conscious perspective that will never be repeated. One brief flash of awareness in the cosmic timeline. That's not insignificant. That's miraculous. You're not small. You're not meaningless. You're not separate from the universe. You are the universe experiencing itself. 13.8 billion years of cosmic evolution created the atoms in your body, assembled them through stellar fusion, and supernova explosions scattered them across space, gathered them into planets, organized them into life, evolved them into consciousness. All of that, all of cosmic history, led to this moment. You reading these words, understanding curved space-time, grasping your place in the cosmos. Gravity connects everything. The same geometry that describes your weight describes black holes devouring galaxies. The same curvature that keeps the moon in orbit determines the fate of the universe. The same principles that make apples fall govern the collision of galaxy clusters. You're woven into this fabric, literally. Your mass curves space-time, infinitesimally, undetectably, but real. You contribute to the universe's geometry. Every heartbeat, every breath, every step you take, you're not standing still. You are surfing the geometry of the cosmos, riding geodesics through four-dimensional space-time, moving at hundreds of kilometers per second through the universe, following paths determined by mass energy distributions across billions of light years. You're not passive, you're not static, you're dynamic flowing part of the cosmic dance. And that, my friend, is what gravity really is. Not a force pulling you down, but the universe itself, curved, dynamic, magnificent, carrying you through space-time on paths determined by geometry. You're surfing the fabric of reality. How cool is that?